essentially very similar to the ordinary equation except for the addition of E1z and E2z. So you know what the reflection coefficient should be. Remember what the Fresnel reflection coefficient are. So it's the same procedure for deriving the Fresnel reflection coefficient, except that now with coordinate stretching we have that two additional terms. So you can write down the reflection coefficient as you remember for Fresnel reflection coefficient quite well. Except that whenever you see a mu2, u2 becomes mu2 e2z. Whenever you see a mu1, mu1 becomes mu1 e1z. So you just have your Fresnel reflection coefficient memorized. Then it will be just very similar to that we know. And K2z, E1z, mu1. So you just multiply mu1 and mu2 by that, K1z, E2z, mu2 plus K2z, E1z, mu1. Okay? And then TTE is just 1 plus RTE, so you just add this numerator and denominator. So E2z mu2 over K1z E2z mu2 plus K2z E1z mu1. Similarly, you can replace the case for Tm, you replace for Tm case, and then it will be very similar, except that you will replace it with mu1, epsilon 2 H2z. Epsilon 1 H1z. Okay, if you repeat that by duality, you can write that down very easily. I won't write that down for you. But let's talk about a case where you can design this interface so that it's perfectly matched so that the reflection coefficient is 0. And let's see how we can define this interface. It turns out that something like this would have to happen, that the two regions will have to have the same impedance as one criterion. And what are the other criteria that you need for perfect matching? So let's design a perfectly matched interface. And I would make the two media the same. This is the first thing I would do. Okay? And then I would match their stretching coordinate systems in the x and the y direction. So I will make this the same in order for that impedance condition to hold true. Ey is equal to Hy. And then let me see if I will get a reflection coefficient that goes to 0. Okay, so if that is the case, then I would have K1z minus kx squared minus ky squared. Am I saying that right? I'm probably not saying it right. Let's assume that let me make some assumption first. Let me assume that the stretching in the horizontal direction are the same in two regions. Okay. So it's the same for the hx. The h will be the same too. Okay. Okay, the H will be the same. The stretching in the horizontal direction are the same. Okay? So let's see if the reflection coefficient will go to 0 in that case. Let me see what the Kz should be. I have this relationship that Ke square is equal to omega squared mu epsilon. And this is equal to Kh squared as well. And the two are actually the same because I assume that the parameters are the same. And if I assume that the Ke squared is equal to Kx squared plus Ky squared plus Kz squared over Ez squared. Okay, if I assume that to be the same, to be that case, I assume that Ex equal to Ey equals 1. But let me assume that Ez to be arbitrary. So if that is the case, then what would I have? I have K1z over E1z. I just want to show that this will become 0. Let me see how I can argue that. K1z over E1z, yeah, that will be 0. Okay? So if this is the case, if I assume that this is the case, Ke squared will be the same as that one, and then I can easily show that since the two regions are the same, and let me assume that this is equal to K1z, E1z, right? But this is also true for being equal to Kx squared plus Ky squared plus K2z squared over E2z squared. Since Ke are the same for both regions, okay? Ke is always equal to this for both regions. I assume that the z's are different, okay? So I will have this thing, and this says that in order for this to be true, K1z squared over E1z squared must be equal to K2z squared over E2z squared. If I have this matching condition, I designed the two regions so that I assume that only EZs are different from 1. The rest of the stretching parameters in the horizontal direction is equal to 1. I have this dispersion relationship that I have proved, which is true for Ke and Kh. Okay, and it's true for both regions. It's true for both regions because since I assume that mu1 is equal to mu2 epsilon 1 equals epsilon 2, I must have this relationship. Okay, so if mu1 equals mu2, the numerator must be equal to 0 because I can divide this by E1z squared E2z squared. If I divide this by E1z squared E2z squared, I will say that K1z over E1z mu2 K2z over E2z mu1 must be 0 because of this condition. Mu1 equals mu2. So this implies RTE equals 0. Can everybody see that? Okay, everybody see that? So I can have a single interface where the two media are the same, but the stretching parameters are different in the z direction. E1z not equal to E2z. I will still have a perfectly matched interface. And this is irrespective of what angle the plane wave is coming in. The plane wave can come in any angle. There will be no reflection at all. Okay? And you can also do the same for Tm wave. Tm wave, I will have this condition, and then I will have perfect matching, and then I will have no reflection. So is this acceptable to everybody? So then you have one degree of freedom to play with. a degree of freedom to change the stretching parameter in the z direction. And yet the wave will not be reflected. The wave will be perfectly matched. So one scenario is that I can have E1z equals to 1 here, E2z equal to a complex number. The wave will come in totally transmitted and there's no reflection, is what it says. Okay? So this actually gives you a very interesting choice because we have seen that kx squared plus ky squared plus kz squared over epsilon z squared is equal to omega squared mu epsilon. Okay, this was the dispersion relationship that we have derived for this kind of media, at least in region 2. This will be the case. Okay? You can pick any epsilon 2, you can pick any E2, this dispersion relationship will be satisfied. Before that we have kx over ex, ky over ey. Now you can have a freedom of choice here. What does this mean? This means that, for instance, I could have a wave that kz is complex. Say if I can do a very simple example, normal incidence. Normal incidence case just for simplicity. For normal incidence, I have this example over here. So I can pick this to be a complex number. Okay, so kz is equal to omega mu epsilon times e to z. This could be a complex number. And kz can have an imaginary part. Can be, say, a complex number with a real part and an imaginary part. And then the wave will have to decay in the z direction. It comes in perfectly matched, but it will decay in the z direction. That is a special case about this modified Maxwell's equation. It gives you a solution to design a perfectly matched interface with zero reflection. The wave comes in at all angles, but the wave will decay in region 2 if you take the stretching coordinate system to be a complex number. Right?
How did you go from that relation to that?
Which one? This one to this one?
Yeah.
Well, this one assumes normal incidence. Normal. Just to illustrate the physics. Okay, the wave comes in normal incidence. But then if you go and look at oblique incidence, you can go back to what we had before. Okay, what we had before for oblique incidence, the dispersion relationship that we had derived, we show that this to be true, that kx is equal to kappa sine theta sine phi, ky is equal to kappa sine theta cos phi, and then you will have k1z is equal to kappa cos theta, okay, and then you have k2z is equal to kappa s to the stretching parameter. I can call this a stretching parameter s2. Okay, cos theta. This is for arbitrary incident angle. Remember we say that if kx equals that, ky equals that, kz equals that, it satisfies the dispersion relationship automatically. But in region 2, you have this choice of K2Z to be kappa times S2. And this could be a complex number. And that complex number allows you to make the wave decays in the Z direction, yet you have zero reflection. Okay, that's the wonderful thing about this. Okay. So we know that in order for matching to occur, Ex must be equal to Hx or Ei must be equal to Hi. And let's call this just Si, the same stretching parameter. So the Maxwell equation that has been modified will look something like this. Let me see. I don't have my paper with me, but what you have then is that you have x 1 over x partial x plus y 1 over sy partial y plus z 1 over x z partial z crossing with E is equal to omega mu h in one equation. Okay. I omega mu, sorry. I omega mu, and then you have veto, the same thing, cross with H, with the minus I omega epsilon E. Right? And then if you were to bring this back to the time domain, how do we implement this? Sx can be a complex number. Okay, it can be, say, A x plus I sigma x over omega. So xx can be a complex number like this. Sy can also be a complex number like this. Ay plus I sigma y over omega. And then Sz can also be a complex number, something like Az plus I sigma z over omega. Okay. So how do we implement this modified Maxwell's equation in the real world? We have to do something called splitting of Maxwell's equations, so that you can implement this with different stretching parameters in the three different directions. And in this case, in order for matching to occur, you know that this has to be true. And then, so how do we implement this set of equations? To do that, we bring them back to the time domain. We bring them back to the time domain, but it's not easy to bring things back to the time domain with this omega in the denominator. Okay, with this omega in the denominator. So you split Maxwell's equation in order to implement. So what you do then is to actually write Maxwell's equations in 3 equations for each of them. So you get actually 6 equations in total. So I divide H into Hxx plus Hsy plus Hsz. Where this means transfers to x, this means transfers to y, this means transfers to z. Okay? So if I look at this first term, the cross product of this with this must produce a transfers to x term. It cannot have any x component. So I conclude that x 1 over xx partial x cross with E, okay, must be equal to I omega mu H xx. I denote this with transverse to x, transverse to y, and transverse to z, yes?
Doesn't the transverse to don't they have overlaps?
Transverse to x,
Transverse to y and transverse to z. You have. I don't see how they can be separated in this one.
okay. So transverse to x, yeah, they would have some overlaps, I suppose. But let me assume that this term is going to match up with this term. Let me split it in this way anyhow, okay? I match this term with the term to the right-hand side. I match the second term with the term, you're quite right, okay, there'll be some overlap. Let me just call this term HSY. Okay, maybe it's not that I'm splitting them that way, but let me call the H field that is associated with this, that is generated by this term HSX. The H field that is generated by this HSY. And then the field that is generated by this term, let me call this HSC. Okay, maybe there's a better way to think about it. That allows me to do that. I just rewrite this as 3 different equations. Then for each of these 3 equations, I can cross multiply. I can cross multiply. For instance, I can write this as x partial x cross with E is equal to I omega mu xx hxx. And then when I have my mu xx, okay, then I would have this explicitly written. This could be written as I omega mu ax minus, and then if I write this out omega mu, I have mu sigma x hxx, right? I would have this. Then I can bring this back to the time domain. This just means partial t mu ax hxx minus mu sigma x hxx. So I have a time domain equation that looks something like this. And this time domain equation can be approximated by finite difference method quite easily. I make a finite difference approximation of the time derivative. I make a finite difference approximation of the space derivative. Very much like what you would do for E algorithm. Except that you have to add this term in. This term is there because of coordinate stretching. And then you can repeat the same for this equation. You can repeat the same for this equation. So all 3 equations can be written in the time domain. And the finite difference time domain method can be used to solve all the 3 equations. And you can repeat the same for the other Maxwell's equation, which is this equation. You also split into 3 equations and write that as 3 separate equations and 2 time stepping with that. And then you can simulate this modified Maxwell's equation in the computer. And when you pick sigma x to be 0, ax to be 1, you're back to the original Maxwell's equation. Okay? So what you do in the simulation is that you pick sigma x to be 0, ax to be 1 in the region that you have the real world. Okay, here sigma x equals to 1, 0, ax equal to 1, for instance. Or sigma I is equal to 0, ai equals to 1. You get the real world back in the middle of the simulation domain. And then you can pick up ax to be different things in the boundary. And as you can see, there will be very little reflection. In theory, there's no reflection when the wave hits the boundary. But because you make finite difference approximations, there will be some reflections in the boundary. And this forms a very, very good absorbing boundary condition. Okay, this is called it coordinate stretching PML. And this idea of coordinate stretching is good in the sense that it can be extended to elastic wave equation very easily. Schrodinger wave. Acoustic wave. So anything that has something to do with wave equation and has something to do with partial x, partial y, partial z, you can do coordinate stretching and came up with stretch coordinate physics equation. And if you choose the stretching parameters correctly, you can get any wave that is generated in the real world to be absorbed by the boundary. Okay. And this has even been generalized to curvilinear coordinate system. Like you can do that for spherical and cylindrical quite easily. Using this concept, you can generalize it to other coordinate systems quite easily. And then there are people who actually see if they can realize this perfectly matched media in the real world. They try to realize it with inductors and capacitors, RLC. I think if you read the work of Zukowski, he tried to do something like this. Zukowski. He tried to replace this with real world parameters to see if you really get something out of this kind of thing. So are there any questions regarding this perfectly matched interface? So no questions means very good. Everybody understood it 100%, right? So I see Mike Wayne nodding his head, so he must be very gung-ho. No. Okay, so if you're very gung-ho about this, then we can move on to a new topic. I'd like to talk about chapter 5 of my book on variational methods. Variational method. I think this is a revision for many of you. So maybe it's a good revision because sometimes you need to listen to things over and again before you absorb it. Right? So second time, third time, fourth time. So if everything is okay with you, I'd like to move on to chapter 5 of my great book. I'll send you this paper after the lecture. If I don't remember, remind me. So I'll talk about chapter 5. Variational method is always based on the principle of optimization, that if you have a solution, the solution can be in the multi-dimensional space, and then you have a functional that is a function of the solution. You try to write a functional so that the correct solution lies in the minimum point. Okay? And then you always want to make the correct solution a minimum of something. It may not be a minimum, but it can also be a stationary point. So it might look something like this. The solution might look something like this. And this is the stationary point. We would like to see how we can use this kind of concept to solve physics problem and electromagnetics problem. Okay? And there are many methods that are based on this kind of concept. FEM, finite element method, is one. Finite element method is based on the variational functional. You can have Galerkin's method. And then you have method of weighted residual. Sometimes this is also called the Petrov-Galerkin's method. I don't know why. And you probably heard of the method of moments too, right? Method of moments. Method of moments. I don't know why it's called the method of moments. If you talk to the statistician, method of moments mean quite different things to a statistician. But somehow in electromagnetics, this is called the method of moments. I don't know why. Maybe Harrington cooked it up. But if you talk to the statistician, method of moments means something completely different. Somebody just won a Nobel Prize in economics for the generalized method of moments to study economics problems. Okay? Not our method of moments that we so often hear about. Those are something to do with statistics. Say if you have a probability function, if you do something like this is usually called the first moment in statistics. This is called the second moment. And this is called the third moment in statistics. Okay? The first moment is usually somewhat related to the mean of this variable x. The second moment, you can deduce variance as standard deviation from the second moment. The third moment, I do not know what. But you can imagine that if you can go on and find the nth moment of this function, you finally will have a lot of information about this probabilistic distribution if you know all its moments. Okay, there's another way of saying it is that if I know all the moments of a function, I know what the function is. Okay? So in statistics, I like to talk about this, but somehow the method of moments is given the name of method of moments for some reason. I don't know who cooked it up. I don't know the history. Maybe he was thinking of some balancing act when he was devising this method called the method of moments. And then there are things like moments of inertia, and then but I think a lot of this work came from Russia. Galerkin is probably a Russian, Petrov is probably a Russian, and a lot of these concepts were in the Russian literature before they surfaced in the Western world, I believe. Okay, but these methods become very powerful in the 60s. Shortly after the invention of the computer, computers was invented around the 50s, okay, late 40s and early 50s, and then in the 60s, then the American methods become very powerful. Okay. But it would be nice to know linear vector spaces in order to understand these variational methods. So I'd like to review linear vector space, or just vector space. I think this can be a repetition for a lot of you, but maybe we just listen to it again. Okay? So if you have a vector space, then the vector space contains sets of elements. This could be vectors, but usually mathematicians don't bother to use overbar to represent vectors. Let's just assume that U, V, W are vectors. Then one of the things that you know about linear vector space is that if U belongs to V, V also is a member of this linear vector space V, then alpha U plus beta V is also a member of this vector space V. And mathematicians like to distinguish vectors different from scalars. These are scalars. And mathematicians have different kinds of scalars. Okay? And these scalars are also called fields. And there are different kinds of fields. Real number, complex numbers, rational numbers are fields. What are special about fields? In a sense that addition and if alpha belongs to a field, beta belongs to the field, addition of the two members also belong to that field. Okay, just imagine if I have a real number, I add another real number, it generates a real number. If a complex number, I add another complex number, it also generates a complex number. If a rational number, which is ratio A to B, integers, if I add two rational numbers, I also generate a rational number. So rational numbers are fields, and also this is true. If I have a rational number, another rational number, I multiply them out, I get a third rational number. So they're closed under addition and multiplication. There's a special thing about fields. Okay? And if you define this to be belonging to a field, and if I have vector U and vector V, alpha U plus beta V is still a member of V. So